Hi, everyone, and welcome. This is 30-Minute Thursday. So this webinar is Surge Protectors for PV Microgrids. So it's part of the Application 101 webinar series. It takes place every other Thursday, so you're lucky that you're here at 3:05 Eastern. So it covers specific market segments as well as surge topics. Hold on. Okay, so this is a companion to the Product 101s that take place every Tuesday. So we call them 20-Minute Tuesdays, and they're helpful how-to guides, descriptions of product ranges, like I just mentioned earlier in this, as well as in-depth looks at the most popular and new products. Also, stay tuned at the end of this webinar. As we've mentioned, there is a gift card game that, although chaotic at times, is a lot of fun. And in order to be respectful of people's time, we've limited the content portion of this event to under 30 minutes. However, the contest and questions may run over, so feel free to jump off if you have to. The contest does have a prize is $19 for the Product 101. Today is a $37 gift card for Application 101. Don't worry about the values. There are 20 and 40, but we bought them on the dark web and they're expiring. We think they're legitimate, but we do recommend using them quickly before they expire any further. Wear a hat, sunglasses, don't loiter around when you try to use them. Maybe you have a car idling. Also, if you're a winner of one of these events and not currently in prison for using one of the gift cards, Tuesday, December 6th is the year-end event. If you are not so fortunate and not already in the contest, we will have a surge proficiency test given on Tuesday, November 15th, always to earn your way in through your wits. There will be $1,937 in total prizes. It'll be just in time for the holiday shopping, or if the authorities catch wind of the scheme, it'll be a good retainer for a lawyer. So good luck and good scholarship.
Okay, so just a couple of housekeeping items before we begin. You'll see the taskbar at the base of your screen. From the left, you can let us know how you're feeling using the reactions icon. The full screen icon is obviously to enlarge the view of the webinar. On the right, now this was mentioned before, but if you're just joining us, you'll see the polls section. If you haven't yet, please take a moment, click through it. That's what it looks like on the screen. Should be 3 simple questions, allow you to participate in today's event and give us some very valuable insight. There's an apps and questions icon as well to the right. To make things easier on everyone, we've turned all those off, and you can direct any comments and questions to the chat, and we can take care of them offline. All right, the gentleman you heard before, his name is Patrick Coyle. He's responsible for the technical portion of today's webinar. My name is Patrick Radler, and I'll be your host. CITEL's claim to fame is we were the first manufacturer of the gas discharge tube. We were founded in 1937 and make the components that are used in our SPDs across all networks. We are active on all the worldwide standard committees and have high current labs on 3 continents. This makes the process of selecting and learning about SPDs easy and convenient. Our corporate office in North America is located in Miami, Florida, and we have a regional office located in Houston, Texas. So with all that being said, I hope you have a paper and pen handy. I'll go ahead and hand it back to you, Pat.
Okay, and welcome back. If you're ready, let's get started. In today's webinar, we'll be talking about surge protection for PV microgrids. We'll learn some key terms and we'll answer some important questions like how to identify the effects of surges on equipment, what are the vulnerabilities we need to be aware of, how do we analyze the risk of lightning and switching, and what really is the electrical withstand of critical devices. And finally, we'll do an overview of the application. We'll discuss selection criteria and recommended products. So if you guys are ready, let's go. So some terms that are important. So surge or transient always. So these are either natural, which is lightning, or man-made switching. They are very fast. So they're microsecond events, which is a millionth of a second. So energy can be up to 200,000 amps. Lightning is more energy, but less frequent. And switching is more frequent, but less energy. So another important term is the unintended surge protective component, or SPC. So when you don't have a surge protector, another component becomes a surge protector. It's the component with the least or the lowest electrical withstand capability. It could be a fuse, it could be the PCB trace that's pictured here, a resistor, capacitor, optocoupler, relay. It could even be a creature scurried up into your cabinet. So a contactor could be microprocessor, a diode. Really, it could be anything, even air in the form of distance. So let's take a look specifically at a circuit breaker, which is an unintended SPC. So it is commonly used in the place of a surge protector. And a lot of people, I guess, mistakenly believe that it offers some surge protection. It really doesn't. Maybe it's because someone reset a tripped breaker after a storm or thought it helped the equipment. It didn't. In surge protection, we do use circuit breakers and fuses, but exactly because they don't really assist in the surge protection function. So we use them to make maintenance easier by disconnecting the SPD in order to replace, for example, a module, also to help limit the current during a fault. The reason we don't offer any assistance is because they're too slow. So in the time that it takes you to count to 3, and Patrick Radler helped me with this. So 150,000 low-level surge just passed through your equipment before the breaker even opens. And
3.
I know you guys are all, can you hear me?
Yes.
Oh, okay. I thought something. So I know you guys don't actually maybe believe me on that. So let's take a look at it in real life and learn about a term that we saw, which was surge let through. So we will impulse here a circuit breaker with 10,000 amp surge and watch the impulse and listen for the tripped breaker. So at this point, if you have your headphones and they're really low and you want to hear the video, you might want to turn them up a little bit. And let's take a look. Listen very carefully. Like I said, you'll hear the surge first, and then we'll see the breaker and hear the breaker trip. Okay. So what really happened here? So we started with a 10,000 amp surge. It traveled down the power line to the equipment, passed through the breaker without any impact. And you started with 10,000 amps at the beginning. And guess what? You ended up with 10,000 amps at your equipment at the end. So this means that even if you had a category 4 rated surface entrance piece of equipment with the highest electrical withstand capability per any standard, it's toast. And it's sort of like the one that I had with my breakfast this morning. So the effects of surges. So how do we recognize them? So we call them the 3Ds. The first is destruction. It's really easy to see. Things blow up. There are charred walls, disintegrated components. The next is disruption. So it generally gets noticed, but usually ignored or misdiagnosed. So when you experience logic tripping, data corruption, hard resets, down links, these are most likely related to even low-level surges. Finally, we have degradation, and that's the premature failure of equipment. Maybe it's not even visible from the outside of the device. Component breaks down internally, which results in a shorter life for the equipment, but nobody really knows why. Destruction is catastrophic, and disruption and degradation are the silent killers. So let's demonstrate the vulnerabilities that we've discussed. And here's a typical cabinet. It could be a panel. You could even think of it as a facility. So in any case, it'll have multiple systems or networks connected to it. So each one has a critical sensitive device that makes everything run smoothly. So look, we can take a look inside. You can see that the equipment is fed or controlled by other more sensitive devices. So there's a LED driver for the lights, the inverter for the solar panels, we have a wireless transmitter for the radio antenna, controller for the HVAC, genset has a controller too, security system and DVR, the incoming utility feed has the main panel, the LAN connection is connected to an Ethernet switch. So this could be one of your cabinets now or a panel that's sitting right inside your building. So there are many different networks that are connected to it. And since we are here for lightning and fun. There's a little bit of an issue. Hold on. PRAD, if you can, looks like there's something on the screen here. I'm trying to remove. All right. I apologize for that. So it looks like we had a little issue with the
There you go.
presentation. It looks like we're back, right? Okay.
Yeah.
So let's imagine that one day, your unlucky day, a thunderstorm rolls in. So in Florida, each square mile has 223 strikes per year. That's the highest flash density in the United States. Texas, not ever to be outdone, is the state with the most total lightning strikes, with close to 42 million. So we can say, so what if, and actually it's more like when, if you live in Florida or Texas, lightning strikes the lighting pole, and you can see the driver is fried from the strike. So this is pretty much an easy one to understand. No protection, large surge, you got no chance. And why? And it's really easy. So most equipment fails at 1,000 amps or less. Most equipment fails with the 4 kV, 2 Ka of the ANSI, the IEC 61000 4-5. It's only rated for 4 kV, 2 Ka, and then the typical component used is only rated at 6,000 to 8,000 amps. So we had mentioned earlier that the average lightning strike is about 20,000, with the maximum being over around 200,000. So here is the not so easy part. You get smart. You place an SPD at the front of the entry, in front of your LED driver, and then sometime in the not too distant future, that pesky storm rolls in again. Lightning arrives as expected, travels down to your equipment, is diverted away by the SPD and put into the grounding system, and poof, there goes your buddy's wireless radio. It fails. But why? Surge protectors divert energy, they don't absorb it. And because all equipment shares the same grounding system, it means that the surges can and will travel all available paths, searching for a good path to ground, and that could be directly through your equipment. Fortunately, the solution is easy. Simply draw a box around your equipment, your panel, your room, or even the entire building, and place a surge protector on all copper that breaks the box. So this will include all wires entering or exiting the box. So we can't predict lightning and other surges. So once we try to figure it out, it'll definitely surprise us. So the one thing we do know is that we can control only what we have control over. So that's how your points of entry are addressed within your cabinet, and how the power is protected. So this is a guiding principle for the box concept. It's a practical tool to use, so please do use it. Like we said, simply draw a box around your equipment, and any wire, copper that breaks or the box should be addressed with surge protection. So now that we sort of understand where we're vulnerable, how do we identify the risks? So the method is pretty simple. We identify possible risks. In this case, we can use something like NFPA 780 to help us. That's a lightning protection standard, but it's been around a long time, and surge protection is in it. Maybe is a little bit limited when we go inside the building, but for the outside, it's a good place to start. So here we can see and a lightning strike, and then watch our two beautiful panels, expensive, fail. So where did this really come from? If we look a little closely, we can see that the lightning strike to the power line. We can see that the power line is feeding a transformer, which is feeding the building, which is also being fed by the microgrid. So it makes sense to me that it came from there, but can we really be sure? So maybe it was something else, maybe a faraway strike. The lightning strike from far away would follow the same path potentially, but maybe with a little bit less energy. It also could be a direct strike to the building with the lightning rods, which is going to have a lot more energy. So risk analysis is about minimizing the threats by examining every possible scenario. And each one, like a faraway strike to our PV array, will have its own unique consequence and, of course, its own solution. So can we survive the identified risks? The simple answer, by using surge protectors at critical points, is yes. The reality is maybe. So there are plenty of standards that are describing how to survive the threats, but how to survive them is a different story. So with so many variables, not only in the environment, but in the tolerances of the equipment and components themselves, for this reason, the SPD standards test without any connected equipment. So it's really just testing the surge protector. And trust me, surge protectors are beasts. So the more equipment living outside in high-risk environments, testing becomes even more critical. But test equipment, like we all know, is very expensive. Same with some equipment that we're testing. The labs are hard to find. It's even harder to find a working lab, but it's really necessary though. So we need to make sure that we can survive the real threats it'll face. And this really requires understanding our equipment. So that takes us to the electrical withstand. So how do we determine the required protection level? So we can start with the standards again. We can look at the IEC 60364-4, and there's a table 44B. So it describes the rated impulse withstand voltage of equipment based on the location in the building. So 4 is the equipment at the front of the building, and 1 is deeper in the building, usually in specialized rooms. We can also look at the ANSI C62 series for a North American equivalent. So it uses categories like C, B, and A. C is the service entrance, B is the branch, and A is the local. So it doesn't really differentiate the equipment in each one of these locations, but only the distance. That's why we tend to use the 44B. It's a little bit better as a reference source. A very important term in this regard is surge remnant. You probably have not heard it too often. So it is the current that is left over after the surge protector has done all that it can. So it's about current sharing. So here we have the surge protector, and the protected equipment. We can see that the surge comes in, a portion of it gets diverted away, and this is what is the surge remnant, the portion that's left over. And this is the critical part about testing is, can your equipment survive what's left over? Because there is a current sharing. The surge protector does not handle 100% of the surge, but what portion of the equipment can your equipment survive is really something that's only sometimes known with testing. So here, if we said that equipment would survive 1,000 amps or less, we would need to have a 90-10 split between the SPD and the equipment. If we used a 10,000 amp surge, that would be 9,000 through the SPD and 1,000 through the equipment. So this is really just the maximum limit, but we really should keep it lower than that in order to extend the life of the equipment. So how do we select a surge protector for PV microgrids? So what are the basic elements of the application? So we have a PV array. We could have some other renewable sources like wind. We have the storage and control, the loads, and a connection back to the AC utility. And we can take a little bit closer look at the application. We can see that there are a lot of various networks connected together to provide the necessary functions for the microgrid. We tend to focus mainly on the power connections, but we can look here and see that there is a lot of data and signal lines as well. So the control is done by smart devices that communicate with other smart devices that are vulnerable too, and they're definitely more sensitive. So this would include your building management unit or BMU, the LAN, energy storage systems. So I know that this looks a little bit daunting. Where do we even start? But we can just go back a little bit earlier in the presentation and remember the box concept. So we're going to draw a box. You can see them here, the red protection boxes around all the equipment or even a structure that you want to protect, and find all the wires that break the box. We can see the power breaking, the signal lines breaking in the inverter. So we need to look really closely at the application and understand the electrical withstand of your equipment and the environment it lives in. So it could live within a building like the managed Ethernet switch, or it could be an integral part of the equipment's control panel. And these are going to have different withstand capabilities. It could even be hiding under your PV panel, and you can find it in the power optimizers that are using maximum power point tracking or MPPT to gain more efficiency for the whole system. So these are tricky little buggers, so we must keep an eye out. So here we can put it all together and apply surge protectors to the microgrid application and get it protected. So this is it. Since this is a PV microgrid, we can start with the PV array. So we'd place a PV SPD in the string, at the string combiner in a junction box within the string, or it could even be at an OEM level and the surge protective components like a gas discharge tube or a varistor that's going to be directly in equipment like the power optimizers that we said we're using, utilizing maximum power point tracking. Next, we can jump over to the inverter, and we can make sure that we place protection at the DC input. In this case, it has dual inputs. It also requires an AC SPD on the AC output, and we can't forget the communication lines. It can be either Ethernet or it can be an RS-45. Next, we can go over to the main panel or the AC bus. This is a central point for connecting the power from all the sources and to the loads. And finally, we can see the smart devices within the building, such as like serial network connectors, maybe some mobile Wi-Fi hotspots, the LAN, the BMU we mentioned, and other controllers. So don't worry about that. It's a lot of stuff. You'll receive some information in the e-brochures later. So now that we understand the protection points, we can go about selecting the appropriate PV SPD for this. And we'll look at this from the point of the UL inspector. So this is a pretty handy tool, this table, for knowing what the inspector is going to take into consideration when evaluating the protector chosen for your application. So keep in mind that a little certification, and especially the right certification, goes a long way. And we can see here we're referring to the 1741, which is the inverter standard. So we saw that last week and how to select. A little bit more in depth on that if you want information. So the UL inspector is going to look at things like the type of UL certification. So it could be DC or DC PV, the type of SPD, 1, 2, 4, or any of the other ones listed here, the suitable ratings for the application, where it needs to be procedure described, if it needs to be updated in the file or requires some additional testing. So we can see that a UL listed device is far easier to use, and where maybe a different SPD needs to be substituted. We can just think of the supply chain issues that we're having today, and also keep in mind that the UL 1449 5th edition is coming up soon. So if you use these type of products with the right certifications, you'll be well on your way. So where can you get this information? The SPD ratings, you can go there directly to the UL website. It's the best place, unbiased opinion or information. So it's in the public domain. It's free. It's very useful for finding the information like the SPD type. We mentioned earlier that the type of system, the right certification, whether it's AC, it's DC, or it's DC for PV. So we can also look at the modes of protection, the VPR, the SCCR, the IN. So it's really an unbiased, handy tool for a source when you're trying to look and find ratings for your information or to compare from different manufacturers. Like I said, in your thank you email that you'll receive today after the event, we put some good references there for you to use as selection guides or more detail on standards. We also have some helpful energy storage and PV flyers that you can get on the website. And as always, go to the website in the search tab and type in whatever you're looking for. So there are items that are specifically related to microgrids and even specific equipment like inverters and power supplies, EV chargers, Ethernet switches. I'm sure you're going to be pleasantly surprised. And if you didn't really get all that, don't worry. You're going to receive this information in your thank you email. So in summary, we learned some important terms like the unintended SBC and surge let-through. We learned how to protect equipment with the box concept. We learned about electrical withstand and a very important term like surge remnant. We analyzed the risk and how to identify vulnerabilities of the PV microgrid. And finally, how to select the right SPD based on the certification and where to find the UL ratings. Remember, choose the correct UL certification and UL will be compliant with 100% of the applications as long as the voltages match the network. With that being said, I'd like to thank you for attending today's webinar. Please hang around for the game and tune in on Tuesday, March 29th at 3:05 Eastern for the webinar that features one of the families, the DS50 VG PVS. It's a PV SPD, and it will be a more in-depth look at specific ratings and features of the series, and will include some destructive tests, which are always fun. So tune in, and thanks again. And PRAD, I think we're ready for the main event.